Two classes ago, we started working on least squares fitting. We started with least squares fit to a straight line. We derived the best least squares fit to a straight line, and we looked at some illustrations, some examples. Last class, we extended that to least squares fit to polynomials. We saw how to extend the matrix method to least squares fit to polynomials, and we looked at some illustrations and examples of that. We also talked about nonlinear least squares fits, so we started to introduce nonlinear least squares fits. Nonlinear least squares fits are nonlinear in the parameters of your model, of your function, whereas linear least squares fits, that means that they are linear in the parameters of your function or your model. In the case of nonlinear least squares fits, algebraic methods don't work for solving the best fit parameters. We have to use an iterative method for solving the best fit parameters. And the iterative method amounts to finding the minimum and the chi-squared where the best fit parameters are found or located. So we talked about various ways of finding the minimum of the chi-squared as a function of the parameters, various ways of descending to the minimum of the chi-squared as a function of parameters. There was gradient descent, there was a stochastic descent, there's a Newton descent. Today's class, I'm going to talk about nonlinear least squares fitting. I'm going to talk about two examples of nonlinear least squares fitting. The sort of classic examples of nonlinear least squares fitting are using a exponential function to fit data. So that comes up a lot, comes up in a lot of different situations. Another classic example is sinusoidal functions. That's a second case where you're nonlinear in the parameters of the fit. It is also a case that comes up a lot. And actually, between the polynomials that we've already discussed and the exponential functions today's class, sinusoidal functions in today's class, most things we end up fitting in physics, many things we end up fitting in physics are made out of those building blocks: polynomials, exponentials, and sinusoidal functions. And so that's the basis of today's class. I'm going to introduce the need for fitting exponential functions and sinusoidal functions. I'll talk about a couple of cases where those fits of an exponential or a sinusoidal function are used to extract fundamental properties of muons that are used themselves to address particle physics standard model. So we'll use that as a sort of example and illustration for today's class. The other thing I want to do in today's class is talk a little bit more about curve fit and the arguments in curve fit. I want to talk a little bit more about the handling of uncertainties on your data points when you're fitting. Talk a little bit more about chi-squared and visualizing, picturing chi-squared, and talk a little bit more about the correlations between the parameters in your fitting. So we're trying to address all those items. Okay, so I got a handful of slides to introduce a couple of physics topics that are related to basic properties of muons, that are related to where fits to exponentials and fits to sinusoidal functions have allowed us to extract important quantities in the standard model, to test the standard model. So one of them is to do with the weak force of nature, which is a universal force of nature. And the second one is due to the magnetism of particles. All fundamental particles are magnetic. And that also addresses sort of fundamental questions in particle physics. So if you think about the forces of nature, well, we got strong force, we got gravitational force, we got the electromagnetic force. And we've got a weak force. So we can list those four forces of nature. Three of them really are responsible for determining the structures of the world around us. So it's sort of at the grandest scale. Gravity is determining the structure of the universe. It's determining the structure of the solar system. It's determining the structure of the galaxy, and so on and so forth. So gravity is kind of the glue that binds together the solar system and the galaxy. Electromagnetic forces, well, they determine the structure of more everyday scales of, atoms and molecules. So they bind together the electrons and nuclei in atoms. They bind together the atoms that make up molecules, and molecules into compounds, and so forth. And then the strong force, that's on a much smaller scale. That's what's responsible for nuclei. It's binding neutrons and protons into nuclei. It's binding the quarks and gluons into the neutrons and protons themselves. The weak force, on the other hand, isn't really responsible for a structure of nature, like the gravitational or the electromagnetic or the strong forces. Rather, its manifestation is that it is capable, unlike any other force, so unique, unlike any force, it can transform at the most fundamental level. It will transform quarks from one type to another type. For example, it can transform up quarks to down quarks and vice versa, strange quarks to charm quarks and vice versa. It transforms neutrons into protons and protons into neutrons, which is nuclear beta decay, basis for nuclear beta decay, and ultimately transforms different nuclei into neighboring nuclei. So I put an example here for between calcium and potassium as transformed through the weak interaction. It drives thermonuclear fusion, and so it's driving the sun, it's driving the stars, and in that sense, the weak force is sustaining our lives. So one of the curious things about the weak force is that every particle of nature experiences the weak force. That's not true of electromagnetic forces, not true of strong forces. Every particle of nature experiences the weak force, and as far as we know, every particle of nature experiences the same strength weak force, and that strength is best determined by the decay, measuring the decay of the muon. And when you measure the decay of the muon, in analyzing your data on the decay of the muon, you end up fitting the lifetime of the muon to extract the strength of the weak force. And so this is a sort of classic example of fitting data to an exponential to extract a fundamental parameter of nature. So we're going to talk a little bit about that type of fit. Just to give you a little more detail, the lifetime of a muon, here's the lifetime of a muon. It is related simply to the strength of the weak force. So this Fermi coupling constant here, Fermi constant here, this is characterizes the strength of the weak force, and this is the measured lifetime of the muon. So if you can measure the muon lifetime, you determine the strength of the weak force, and that would be done by fitting a time distribution of muon decays to extract the lifetime, and therefore determine the Fermi coupling constant. This is just a picture, because I know about it, of an experiment that was used to measure the lifetime of a muon and extract the Fermi constant to very high precision, to very high accuracy. So the lifetime of the muon is measured to a part in a million, and the strength of the weak interaction is determined from that to about half a part in the middle. So it's a very, very precise measurement of muons. Basically, a beam of muons is injected, pulse beam of muons is injected into a target material, and they stop in that target material and basically prepares a source of muons for you. Beam comes in, stops in a target, the beam goes off, you've got a source of muons, like you might have a radioactive source. You then detect the decays of the muons by detecting the electrons that the muons decay to. So you see a lifetime of electrons emerging from that target that you've loaded up with muons. You see the electrons coming out, and these electrons are decaying away with the lifetime of the muons. And so you measure the time distribution of the muons, of the electrons. And from that, you can determine the lifetime of the muon. Here's the data from that experiment. This is measured data. In black is measured data points. It's a huge statistics of measured data. So it was 10 to the 12 decays were measured in the experiment. So enormous statistics. So you can't see the error bars, can't see the uncertainties on the data points. Then that is simply fit to an exponential decay curve. And from that exponential decay curve, that's the red line here, the muon lifetime is extracted, strength of the Fermi constant is extracted, and that becomes a basic fundamental parameter in the standard model. So just a basic measurement of a lifetime to high precision in the muon case determines a very important parameter in the standard model. The other case I wanted to mention, which is related to the other type of function, I said to talk about sort of sinusoidal functions, fitting sinusoidal functions. This is related to the magnetism of fundamental particles. So, you know, atoms and molecules have in general magnetic moments. They're magnetic. Protons and neutrons, electrons and muons, they're all magnetic particles. They have magnetic dipole moments. And quarks and electrons, they're magnetic. So all our fundamental particles, all our basic building blocks of matter at all levels around us are built out of magnetic particles. So it's a very important thing. So the quarks and the gluons have what we call intrinsic magnetism. So they're, as far as we know, they're fundamental particles, but they carry some magnetism. A large portion of their magnetism is predicted by kind of relativistic quantum mechanics. So the Dirac equation predicts that charged particles will have a associated charged spin half particles will have associated magnetic moment or magnetism that is determined by their charge to mass ratios. So that comes out of the standard model. That's a picture, that's a prediction of the standard model that is verified. So there's this large contribution to their magnetism from that basic fact. In addition, we now know that the vacuum is not completely empty. The vacuum is kind of teeming with these particles and antiparticles that are being constantly created and destroyed. So if you were to look in the vacuum, you see these positrons and electrons that are appearing and disappearing. You see quarks and antiquarks appearing and disappearing. In fact, you just see all the flavors of particles in nature appearing and disappearing within the vacuum. So that's sort of boiling away at the vacuum with electrons and positrons and quarks and antiquarks actually also contributes to the magnetism of the elementary particles. So to the direct contribution to the magnetism of the elementary particles that's just determined by their charge and mass, there's a much smaller but significant contribution that comes from what's going on in the vacuum, all this activity in the vacuum, all these vacuum fluctuations with electrons and positons and quarks and antiquarks. That piece of the magnetism of the elementary particles is called the anomalous magnetism of the elementary particles. So an electron has a magnetism, it has a magnetic moment. There's a direct contribution to that magnetic moment that's big, and then there's a small anomalous contribution to that magnetic moment that reflects the vacuum fluctuations that are going on in the vacuum. The muon likewise has a direct contribution to its magnetic moment. That's the big part. Then it has an anomalous piece, an anomalous contribution that comes from all these vacuum fluctuations that are going on in the vacuum. It turns out that in the case of the muon, and it's even better than the case of the electron, you can measure accurately the anomalous piece of the magnetic moment. And you can compare it with your understanding of the vacuum fluctuations in the vacuum. And you can, in that way, test the standard model of particle physics. So you can test a model of what the elementary particles are. You can look for evidence of other particles beyond what we know there are. And so the muon's anomalous magnetic moment is an important test of the standard model. It's an important test of vacuum fluctuations, and it's an important constraint on particles that are beyond the standard model, particles that we don't yet know. So the way you would measure the muon's anomalous magnetic moment is you put muons in a magnetic field. Muons in a magnetic field will experience a magnetic torque. Those muons will precess, and the larger their magnetic moment, the faster they precess, the smaller their magnetic moment, the slower they precess. So the precession frequency allows you to measure the magnetic moment. The signal you would see is a precession signal, a sinusoidal signal that would allow you to determine the magnetic moment. This is just a little bit of detail to show you. The muon's anomalous magnetic moments, given the symbol A, the anomalous magnetic moments are given the symbol A. The muon's anomalous magnetic moment is given the symbol A mu. Its predicted value in the standard model is given this symbol A subscript u superscript standard model. And that prediction arises from several distinct contributions. One of the contributions is from vacuum fluctuations involving electrons, positrons, and photons. So that makes a contribution. This is a picture of it, and that's the big contribution. Another contribution comes from the weak force that we talked about. So it comes from the weak force is carried by force-carrying particles called W bosons and Z bosons. It involves neutrinos. And so there are contributions. Here's a diagram of one from the weak force. There's the quarks and gluons in the vacuum that are appearing and disappearing constantly. So they make a contribution too. This is a picture of their contribution. So they're contributing. And then the big question is whether there's something else in the vacuum. There's something else in the vacuum that we haven't yet seen in experiments. Something else in the vacuum, whatever it is that's in the vacuum, will contribute to the magnetism of the muon, the anomalous piece of the magnetism of the muon. And so this is what we're really chasing in measuring the muon's anomalous magnetic moment. The way the muon's anomalous magnetic moment is performed is basically when we measured the lifetime of the muon, we stopped muons in a target and watched the decay electrons, measured the decay, an exponential decay curve. In measuring the magnetic moment of the muons, we inject muons into basically a magnetic bottle, magnetic storage ring, and they orbit around in that magnetic storage ring. This is the storage ring. The muons are entering upstairs here, and they circle around. And so they're circling around in a magnetic field, and they precess. We said their magnetic moments will interact with that magnetic field. They'll experience a torque that calls the precession, and we can measure the precession signal, the muon magnetic moments rotating, the muon spins rotating, by again measuring the electrons that come from the muon decay. They carry the information of the direction of the spin. So that's basically how the experiment is done. And here, just to show you the importance of a fit to a oscillating signal, sinusoidal signal. This is the data from that experiment, or at least in black data points. Again, the statistics are super high because the precession here is measured very, very accurately. In red is the fit to a sinusoidal precession signal. It's the these wiggles here, and there are hundreds of them, the muon spin rotating around, precessing around. And by measuring this frequency, by fitting this sinusoidal signal, you can extract the muon's anomalous magnetic moment. And in that way, determine the contribution of the vacuum to the muon's magnetic moment, and test for particles beyond the standard model, or the test the quality of the standard model. Okay. Well, I wanted to give those two examples to just demonstrate that fitting an exponential, fitting a sinusoidal signal, both of them are common things we do in analyzing experiments. And in some cases, just by fitting an exponential or fitting a sinusoidal signal, you can extract important underlying quantities about nature around us. We're extracting here the strength of a universal weak force that every particle experiences from fitting in an exponential. We're extracting here the nature of the vacuum fluctuations from fitting a sinusoidal signal to the muon's precession. So from fits to sinusoidal signals, fits to exponential decays, you can extract fundamental information. Okay. So we're going to do some fits to exponentials and sinusoidal signals. I'm going to actually kind of, rather than use real data, because real data comes with some complications, I'm going to simulate data. I'm going to imagine simulating a particle decay experiment, imagine simulating a magnetic particles precession experiment, and then we're going to fit that data with exponentials and with sine waves. Remember, these are now nonlinear fits, and we're going to use curve fit, and we'll be under the hood, we'll be using various descent, chi-squared descent methods like gradient descent or Newton descent to find the minimum chi-squared and to find the best fit parameters. And if you want to do this precisely, you want to extract the muon lifetime precisely, or the muon precession site precisely, because you want to determine the strength of the weak force precisely, or you want to determine the contribution of vacuum fluctuations precisely. And we've got to be careful, and we've got to be thorough about our fitting procedure and about using our curve fit. Okay, so we're going to go on and use curve fit today. I just grabbed some the description of curve fit, and I just wanted to walk through these arguments here that we'll be using, and then we'll go to my code. So when you call curve fit, and I think you've already called curve fit, but when you call it, there's a series of arguments that you call it with. The first argument is the name of a function. This is the name of a function you've written, typically. It's the name of a function you've written, which is your model, your particular model for whatever data or whatever, whatever data you want to fit. You build a model, that model is encapsulated, built into your function. And that's the first argument in your curve fit. And we talked about in the last class, you want a model that will neither underfit, it has something missing in it, or overfit, it has too many parameters in it. You want a model that's tailored to your particular data. So that's the first item in the model. The second two items are the data. So the data are typically pairs of independent variables, X and Y variables. And so those are the next two arguments. The fourth argument in this list here, which is an optional argument, but often an argument we would give, is your model has some parameters. You've given passed the function name for your model, your function, but it has some parameters, and you can give curve fit the initial guesses for those parameters. Remember, we're going to be doing some sort of descent to the chi-squared minimum, and all of the descents that we talked about, whether it's gradient descent or Newton descent or stochastic descent, you start at some location. You have some initial location, some initial guess in chi-squared space that you're going to start at, and you're going to work your way to the chi-squared minimum. So you can pass that initial starting point as a guess. We also talked about in the last class of it, but it's going to be important in this class, something else that we want to pass about the data is the uncertainties on the data points. Two classes ago, we began with the equal uncertainties on the data points. We didn't even worry about the uncertainties on the data points. We fitted as if treating each data point as equal. We would call that unweighted fit, where every data point from the first to last is equally treated. We're in this class going to be treating our data points depending on the uncertainties on those data points. So if there's small uncertainties, we want to weight them more. If we have large uncertainties, we want to weight them less. And so we have to pass to curve fit the uncertainties, the standard deviations on the data points. That's this argument. Okay. I think that, yeah, that's everything I wanted to say. I'm going to go to the code, and we'll look at some examples of fits. Okay, so as an example of a fit, I've taken an example of fitting for the lifetime of a pion, fundamental particle. The example I gave was fitting of the lifetime of a muon, another fundamental particle. But both of them, their lifetimes have been measured by measuring their decay products, and both of their lifetimes have been measured accurately. The muon more accurately than the pion, but I'm taking the pion as an example here. I'm taking the pion here as an example, actually, because we have the code, and you have the code for simulating the decays of the pions from previous earlier work when we did Monte Carlo, when we did random numbers and random number sequences. So you can, for the assignment, for example, and for this example here, I just took my old code for creating pion decays, and you can just take your old code for creating pion decays for the homework assignment. Okay, so I think I'm going to show you three cells here. The first cell I'm going to go through quickly because it's really just cut and paste from when we simulated Monte Carlo methods, random numbers, pion decays, some classes ago. So I'm just going to simulate some pion decays. So I'm going to create some data on pion decays rather than try and read in experimental data on pion decay. So that's going to be the first cell. The second cell, I'll actually be calling curve fit. We're going to call it multiple times as we start to address how to properly treat the uncertainties in the curve fitting. And then the third cell I'm just going to use to look at chi-squared distribution, the chi-squared landscape, you might call it, and also talk about correlations, things like that. Okay, so I'm importing the packages I need for plotting, for fitting, for arrays. And now I'm going to simulate a pion decay experiment. In which I'm simulating a measurement. It's going to be a measurement of the pion lifetime. So there's a bunch of parameters that I've set associated with this. The pion lifetime is measured, is 26 nanoseconds. It's measured to about a part in 10,000, I think. So here's the lifetime. And I'm going to use that if I'm going to simulate the pion lifetime. I'm going to simulate the measurement of a time distribution of pion decays. And so if I'm measuring a time distribution, if I'm building a time histogram, I'm going to specify the size of the time bins. I'm going to specify the time range of the histogram, and I can calculate the corresponding number of bits. And so that's what I've done in these three lines here. I've got 26 nanosecond lifetime. So I took time bins at a 1/10 of a nanosecond. That made the lifetime of the pion, some hundreds of bins. So that the bins are fine compared to the pion lifetime. I wouldn't want to fill bins where the bins are coarse compared to the pion lifetime, because I might worry about the accuracy of the fit. I've got 1,000 bins of 0.1 nanosecond. So the total range is going to be 100 nanoseconds. So that is about 4 pion lifetimes. So there's not going to be many pions left after 4 lifetimes. So I'm collecting most of the data on the pion decay. So almost no pions are going to survive beyond this 100 nanoseconds. When we talked about the Monte Carlo method before, we talked about we would generate pion decays. Pions are going to decay to muons. We would test each pion whether it decays to muon in each tick of our time bit, in each clock tick. And what determined the probability of a pion decay in a particular time interval, the clock tick or the bin width, was the ratio of the bin width to the lifetime of the pion. So that's this probability here. So bin width is 0.1 nanoseconds, and pion lifetime is 26 nanoseconds. So this small number is the probability for any particular pion in decaying in each time bit. And I'm going to use that. What I'm going to use it for is I'm going to imagine starting with some sample of pions. I'm going to start with 10,000 pions. I'm going to watch them decay to muons. They decay into muons, or almost all of them decay into muons. We're going to start with none of them having decayed into muons. So I've got n pi is my 10,000 starting point for the pions, and mu is my 0 starting point for the muons. I'm going to set up some arrays here. A array time that is kind of my proxy for the independent variable time. And then I've built these 3 arrays here. I'm just initializing the zeros right now. That are going to store the number of pions that have survived as a function of time. So that's n pi. Store the number of muons that are accruing as a function of time. So that's my NU array here. And then most importantly for the experiment, I'm going to store an array that contains the number of decays that are occurring in each time bit. So ions are decaying into muons. In the experiment, what do we record? We don't count the number of ions. We don't keep counting every time bit. We don't keep track of how many ions there are. We don't keep counting the number of muons. Every time bit, we're not counting the number of muons. Rather, what we're counting is we can see the decays themselves. We see the moments, we record the moments, count the moments when a pion decays to a muon. So this is what we would actually see in the experiment, the number of decays. Okay. So now I've set up my arrays to store the information that my Monte Carlo using random number sequences is going to generate for my pion decays to muons. The filling of those arrays, the generation of the data, the simulation of the experiment is basically contained in these group of lines here. It's contained in this for loop. Actually, these nested for loops here. The outer loop is a walk through the time steps, time intervals in my time distribution. So I think I have a range of 1,000 time bits over 100 nanoseconds. So I'm going to take 1,000 steps through this outer loop. Each time I walk through the outer loop, for each of those steps, ultimately, the most important thing to me is to record how many pions decay to muons in each of those steps, because that's what I'm would observe in an experiment, and that's what I want to record in the simulation of an experiment. How many pions decay into muons in each time bit, in each time interval. So I'm initializing this counter here. NDY for the number of decays in a particular time bit. After that initialization, to record the decays of this time bit, I'm going to walk through the individual pions and ask each individual pion, did he or she decay in this little time interval, in this little time take? So the first time I go through the loop, I'll be asking this question to my entire collection of pions. But as time evolves, because pions are decaying, muons are accruing, I'll only be asking this question about the surviving number of pions. So I've not only got to count the number of decaying particles, but I must keep track of the number of surviving pions, because only those ones can later on decay. Okay, so we start walking through our pions, and this is where I implement this decay probability. I generate a random float from 0 to 1. If it's smaller than the small probability, as the signal that a pion decay, and I'll increment by 1 my pion decay counter for that time bit. And then after I walk through all those pions decayed in that little time bit, figuring out the total number of decays I got, I better decrement the number of pions that have survived, because we just lost some of them, and increment the number of muons because we just gained some of them. So I increment and decrement these numbers. And then because I want to build time distributions, I fill the current number of pions into the pion array, current number of muons into the muon array, and current number of decays in this time bit into my decay array. So I build these arrays up. There's one more thing after done my simulated experiment. I generated my simulated data. And that I added to the simulated data was I generated this additional array. I wanted in this cell, I just wanted it for plotting to give us an idea of the scale of the fluctuations on our data. I wanted the scale of the fluctuations on the data, so I took the square root of the number of counts in each time bit as an indication of the statistical fluctuations that I might, when I do this experiment, that I would expect. So if I simulated many times, I could map out these statistical fluctuations. But here I just calculated them approximately with basically Gaussian statistics, and the square root of the number of decays is kind of a measure of the statistical fluctuations. So that's, I think, the one line that I really added in this cell when I stole this cell from my Monte Carlo method, random number method, simulation that we did earlier on. And then I just make a few plots. This is just checking that things make sense. So I didn't show you the course of the plotting functions, but in red here, according to the legend, these are the number of surviving pions. So we started out with 1,000, and we said by the time we get 100 nanoseconds, because of the 26 nanosecond lifetime, we expect hardly any. There will be a few, but hardly any. The blue is the number of muons. We started out with 0. We sampled as all pions, but the number of muons that are going through is a function of time. It's the pions decaying at muons. So we see that losses of pions are gains for the muons. These are the number of decays as a function of time. So for each time bin, there was a change in the number of pions and a corresponding change in the number of muons. That was the number of decays. And here I'm plotting the number of decays. So these are much smaller numbers. So in the first time bin, when we had 10,000 pions, we had something like, I don't know, 20, 30, 40 decays. There's a small probability, the chance of 0.1, the bin width, divided by 26 nanoseconds, the pion lifetime, for any individual pion decay in a time bin. So even in the first few time bins, the number of decays are, tens and 20s and 30s and 40s, that sort of scale. And as time elapses, right, and we have less and less surviving pions, we have smaller and smaller numbers of decays. And towards the right-hand side of this graph, after 100 nanoseconds, we've got very small numbers of decays, just a few decays in each time bit. These data I plotted as data points with error bars on. Just to give us an idea again, that these, if you repeated this experiment, the second time, a third time, many times, you see fluctuations, statistical fluctuations in your data, and the square root of the number of counts, sort of a measure of the statistical fluctuations. So you're seeing here that, the square root of 49 is 7. So that would be the scale of the error bar on these initial points here. And when you get out here over on the far right, where you've just got handfuls of counts, well, then the statistical errors on the data points are fractionally much larger. Anyway, so that's the simulation of the experiment of the decay data. Yes.
Did you mention why the error bar should be the square root of count?
Yeah, I'm going to come actually on the next cell. I'm going to say a lot about that. I tried to say when I was describing it in this cell that it's sort of approximately the uncertainties on the data points. So Gaussian statistics, you have Gaussian statistics, then the Gaussian counting statistics. Then if you had a mean number of counts of 100, if you repeated the measurement many times, then the statistical fluctuations would have a standard deviation, the square root of 100, they have a, which would be 10. So they fluctuate by that amount. So that's Gaussian statistics. If you have small numbers of counts, so maybe you have not 100 counts, but you have 10 counts, or you have 5 counts, or you have measure 1 count, then this square root of the number of counts argument starts to break down. You have to be more careful. So what you anticipated is that I really want to talk about that, because this is a case where this is very important. We don't even have 100 counts to start with. And so this idea that these error bars of the square root of the number of observed counts is, it's probably okay over here. It starts to really be not okay over here.
Does that also like come from Poisson statistics?
Yeah, so Poisson statistics, Gaussian statistics are a limit of Poisson's statistics. If the average number of counts is large, so let's say 100 for the facts, then the Poisson distribution starts to look like a Gaussian distribution. And so Poisson distribution evolves into a simple functional form, a Gaussian distribution for large statistics. Low statistics, if you have 0, 1, 2, 3, or whatever counts, or 10 counts, then the distribution, Poisson distribution, does not look like the Gaussian distribution. We have to be more careful. At this stage, the reason I put the square root of the observed number of counts at this stage is if you just measure the data, right, and you've not done anything with the data, that's the only, that's the best guess you can make, is that the uncertainties on the bins are the square root of the observed number of counts. But as we start fitting the data, we'll see that you can make better approximations for the uncertainties on the data points and do better than this. Okay. In this cell, then I'm going to do the fitting of that exponential decay curve. And I'm actually going to call curve fit several times to fit the exponential decay curve. I'm going to call it several times with different approaches to handling the uncertainty. So exactly the problem that you raised, and then you had suggestions for. So we're going to call curve fit several times, but with an increasingly sophisticated treatment of the uncertainties, which is important if you want to extract say a lifetime of the pion with good precision. Before I do the course of the curve fits, just a few things, quantities I introduce here. We need to define a model. So I've got to define a model that I'm going to fit. It's just an exponential decay, and it's defined by this user function here. The arguments to the user function are the first argument is the independent variable, so it's the time. Second and third arguments, or the remaining arguments, are the parameters in your model. I've just got I'm just modeling with an exponential decay. It has one parameter, which is an overall normalization of that curve that would change if you had more or less pions when you started. And then the second parameter is the lifetime of the decay constant. And so these are these two parameters here. It just returns under the hood in curve fit. Curve fit is just going to be past the name of this function. Under the hood, curve fit is just going to, be calling this function as it tries to find the chi-square minimum. So this function, when curve fit calls it, this function just returns the value of the function for the times and particular values of the parameters that we're trying to find the best fit values for. Anyway, so that's my function, and ignore this, we might come back to it. There's two other things I defined here that were kind of handy to me. And this is just a record of the number of parameters in the function, so two. These two parameters here, nmin and max. I did build into this code the ability to fit over not the full range of the data arrays. I could fit over a restricted range. Actually, in the examples I'll show you, I didn't really use that, but it's a useful thing to build in. And so I defined these. This would be like a start. A better name might have been start time and end time of my field. If I choose these numbers in all the code below, I use slicing so that I could change the start time and the end time of the thing. Okay, so basically got a user function there, and some sort of handy other little things. I got the full curve bit here upstairs in the cell. Got another colored curve bit down here. This is in the middle of the cell. There'll be more cores down below. I've got to scroll down to. First one is I just called curve bit with my model, with my independent variable and my dependent variable containing the data. Remember the false argument was the parameters, the initial guesses for the parameters, because we're doing gradient, there's some sort of descent. We need an initial starting point. This is how you pass this argument with this key here, and then it expects a list of the initial guesses of your parameters. So I just constructed the list here. Or you could construct it beforehand and then just pass a variable that is the list. And this just tells me I'm using absolute rather than fractional uncertainties. This is where I put in the slicing. If later on I wanted to change the range of the fit, if I wanted to change the start time and the end time of the fit, I could use my nmin and max. So this is called, and it's going to return two items here. One is a vector. This is the parameters vector. In this case, it's just the two-element vector with the two parameters, a normalization parameter and the time constant parameter. And then it also returns a covariance array, if you remember that. The diagonals on that array are the squares of the uncertainties on the parameters, and the off diagonals, they measure the correlations between the parameters. They're the covariance between the parameters. So that's what gets returned. Now, actually, important thing here, when I called this function, I didn't specify the uncertainties on the data points. That was a fifth argument. It's going to treat that as I'm going to do an unweighted fit to the data. This means I'm going to weight every data point with the set as if it had the same uncertainty. Now, counting statistics, that's going to be wrong, first of all, because we saw when we estimated the uncertainties that they had, different sizes when you had early times and higher statistics decays, and later times when you had smaller statistics decay. So it's wrong to fit the data with equal weighting. And we might expect it would introduce what we generally call a bias. It's a bias because, early times and late times of the time histogram, we're making a bias from the true uncertainties by just treating every data point equally. So it's likely that it would bias our extraction of the model parameters of the lifetime or the normalization. So anyway, this was just a comparison. After I do the call to curve fit, I'm going to calculate these things each time. I can call the function, my user function, it was fdy, with my time array. And what it will return is the best fit data. The curve fit is done using the best fit parameters. So this is the best fit to my line, to my model. From that, the difference between that and the actual data, which is this second line in this block of code here, this difference that's the difference between the data and the models fit to the data. That's what we call the residuals in the last class. Those are the differences, the residuals between the model and the data. And so we calculate that. And if you remember, we said if you square that up, that represents kind of the length squared of the residuals, that's the chi-squared. And if you were to divide it by the number of degrees of freedom that you have in your fit, which is the number of data points less the number of parameters, that gives the chi-squared third degree freedom that's used as a measure of the quality of the fit. I'm going to calculate all those four things. Maybe you can think about the data as a vector in data space. You can think of the best fit as a projection of the data onto the model space. So this is like the data, this vector here is a projection of the data in the data space onto the model space. You can think of the residuals as another vector that's orthogonal to the model space that wasn't that the model space wasn't capable of describing. So it's a vector that's orthogonal to the model space, and the basis vectors of the model space. So that's one way of thinking about all these things. Then I print out the results. Now I'm going to follow that procedure several times. This is my second call to curve fit. Now, this time I'm reminding myself that I've already estimated the uncertainties on the data points. So I estimated the uncertainties on the data points based on Gaussian statistics and the square root, the uncertainties being the square root of the observed number of counts. Remembering that we had this discussion that we said that that's an approximation. It's the best I can do, right? So I define this vector here S that contains the standard deviations. And now when I passed the arguments to curve fit, I've added this fifth argument here, which is the keyword is the sigma here, which and then it expects a correspondingly sized array to match the independent and the dependent variables here with the uncertainties on the data points. So now this will be a weighted fit. It's going to weight according to the uncertainties on the data points. So I call that, and I calculate the same vectors here, right? calculate the best fit vector, which is the projection of the data from the data space into the model space. We calculate the residuals vector, which is the component of the data vector that isn't expressed by the model. It's going to be perpendicular to the model space. And then I calculate the chi-squared and the chi-squared per degree of freedom, which is a discriminator for good fits versus bad fits for the quality of the fit. Calculate all those things and print it out. Okay, then I'm going to have one more section where I'm calling curve fit. And this third block of calling curve fit is here. Sorry. Is here. It's a little more complicated because I can call curve fit here multiple times in an iterative loop. The idea is that the proper way of estimating the uncertainties on the data points, that is improvement over our current uncertainties on the data points, which is the square root of the observed counts, is to actually, what it should be, what Poisson statistics would say, is that the uncertainties on the data points is the square root of the predicted value, the model value for the counts at that in that particular bin. So if just think about a number of neighboring bins, and the number of counts in those neighboring bins statistically fluctuates. But if those neighboring bins are very nearby, and their lifetime is much longer, then you would expect that those neighboring bins would have very, very similar uncertainties. Whereas if you're using the square root of the number of counts that you observed, which has the statistical fluctuations in, then you'll get statistically varying uncertainties. So the true uncertainties shouldn't vary statistically. The true uncertainties should be a measure of the true fluctuations, which should vary smoothly across your histogram. Here's an extreme of it. So think about towards the end, the right-hand side of the histogram, large times in the histogram. In that region, you might have bins, maybe have a bin that has 2 counts. Maybe you have a bin that has 1 count. Maybe you have a bin that has 0 counts. So we've got very small numbers of counts out there. And we've got bins that have 0, 1, 2, 3 counts in them. Well, if they're nearby, the actual decay curve, the model would say that they would have very similar statistical uncertainties. We're just seeing the fluctuations. But if you use the square root of the number of counts for the uncertainties, you're going to get the square root of 2 or the square root of 1 or the square root of 0, which are very different numbers. In particular, the square root of 0, which is 0, says that if you've got 0 counts on a bin, then if you're using the observed number of counts, there's no error on that value. So that's saying that this is a really important point to weigh, because it has by far the smallest uncertainty. And that again will bias your fit. So you don't want to do that. So this is a typical way of getting around this, right? After the previous fit, we do come out of the previous fit with some estimate. We now have not just the data points, but we have a function through the data points. So the next time I call curve fit, I'm not going to use the square root of the observed number of data points. I'm going to use the square root of the fit function. I'm going to use that because that'll be a smooth function going through those bins where it went like 1, 2, 3, 0 counts. It'll be a smooth function through that. So this is going to be this correctly handles the Poisson statistics and doesn't base our estimate of the standard deviations on fluctuating numbers. So we're going to use that. I do that several times. You see, I go through this loop several times. You could do it 2 times, 3 times, 4 times. I do that because, you know, you could imagine the first time you go through that, you're going to update the function. when you come out of it. You've refit with more appropriate errors, kind of remove some of the bias, so you'll get a different function out. So we better go back through again, check with the new, when we have the new function to calculate the uncertainties on the data points, we better refit. So you would typically do this several times until you kind of converge that the function is no longer changing. And then you can only do that a couple of iterations, 2 or 3 iterations. So that's what I did there. Anyway, so those are the cases I fit. I did unweighted. That was the first case. You said that's going to have bias. That's going to have bias. We did weighted with the observed number of counts. We said, well, that's probably going to have bias too. We were worried about these bins that have no counts. And then we did this iterative use of the fit function to estimate the data, which correctly deals with Poisson statistics. Okay, so I won't go there. I made a plot of the fit, the final fit. This is. So I'll see that here is the read the data again with the these are the, I think these are now, I wonder if I'm plotting the right error bars. Yeah, I am. Yes. We recalculated S each time. So these error bars on here now are updated error bars. These are based on Poisson statistics. It's probably hard to see a difference, but if you have 0 or 1 counts, you're going to have the same error bar. So this is in blue buried is the best fit through the data. It looks like a good fit with the data. And then in green here, these are the residuals. These are the differences between the fit and the data. And this is really the residuals vector, this large residuals vector. That is the component that's orthogonal to the model space, but it's just noise. That's all we're seeing orthogonal to the model space. We're not seeing any systematics here. Upstairs is my printout from these 3 steps that we took in increasing sophistication of the fitting. The first step was unweighted data points without specifying any uncertainties. We got remember the true lifetime, kind of the truth in our simulation was 26 nanoseconds. That fit gave 24.8 nanoseconds. The quoted error bar here is 0.16 nanoseconds. So this is many standard deviations from the true. So something went wrong here. What went wrong here is the biasing that came from the unweighted uncertainties and the wrong choice for the uncertainties made this chi-square, the degree of freedom, which should be around 1. We then updated to the square root of the observed number of counts. Okay? So when we did that, we're approximating the uncertainties on the data points, and that's fixed the chi-square. The chi-square is now sort of an adequate chi-square. But if you look at the fit still to the lifetime, I think it still has bias, right? Now we said we imagine it will still have bias because the 0 counts in a bin, it's overweighting that point. It's going to pull the curve down. I think that will shorten lifetime where you get 0 counts. And again, we see that with those 24 nanoseconds to a lifetime, that is several sigma away from the true lifetime. Then we did the procedure of making better estimates rather than using the data, use the fit function for the uncertainties. And so after doing that, we get an adequate chi-square. So this is a discriminant fit being okay. The lifetime is now 25.5 nanoseconds plus 0.7 nanoseconds. So this was within a standard deviation of the truth. So this looks like it's no longer has a bias that was present in the other two results. The third cell, I don't want to walk through the code in the third cell because it's just plotting. It's just me plotting the chi-squared. I just want to show you the results. So in the third cell, I now know my best fit values for the two parameters in my fit, for the normalization parameter and for the lifetime parameter. So I know those two parameters. And this cross point here marks the value of those two parameters. So the best fit normalization was about 39, just below. And remember the lifetime was about 25.5 nanoseconds. So that's this point here. This is the results of curve thing. This region here is the chi-squared just as a function of the parameter landscape. So the horizontal axis is lifetime. The vertical axis is the normalization parameter. These are the two parameters in the fit, parameter one and parameter two. And we're seeing the value of chi-squared as a function of these two parameters. So I just called the I just calculated the chi-squared over a grid of this range of the parameters. This is hard in the slide to read the color coding, but dark blue region here, that's the lowest chi-squared down here around 440. Then as you go to yellow, 530, that's higher chi-squared down here and up here. So you're seeing kind of the valley of the chi-squared in this. One thing you're saying is, you maybe not seeing it, that if there's a dark blue oval here, and there's kind of ovals of different shades that emerge from that. So these two parameters are correlated with one another. And you see this correlation in the parameter. You see this kind of oval shape. You can also see that correlation in the covariance matrix. So remember the curve fit returned the covariance matrix, and this is just a picture of the covariance matrix. It's a rather silly one because it's only 4 elements in the covariance matrix. But these diagonals here are the squares of the standard deviations, the uncertainties on the data points, and these guys represent the off diagonals correlations. And these correlations, right, are as large in size as the standard deviations. That is, these points are the normalization parameter and the lifetime here. The way that we've set up the model are highly correlated with one another. If you shorten the lifetime, you'll tend to increase the normalization parameter. You could maybe imagine that. Supposing this is the lifetime curve, if I shorten it, the way the fit's going to compensate is by making the normalization parameter larger. So these are negatively correlated, and you see that there. I've run out of time, so I won't go through the other plot. I just show you the pictures. I did a similar thing for fitting a sine wave with some. So this is some mock data I generated in a cell. I did the same procedure for fitting the data, and I went through these same steps. Remember, unweighted fit, you get a bias. Weighting based on the observed number of counts, you'll get a bias. I work my way through to fit based on uncertainties based on the fit function determining the uncertainties. So that's what I did there to get the good fit. And then I went and look at the case, the dependence on the parameters. In this case too, if you fit a sine wave, I'll promise to another this, fit a sine wave, supposing you've got the amplitude of the sine wave, and then you've got the sine wave has a frequency to it and a phase to it. the frequency and the phase also tend to be, you have to watch out for the correlations there. You could imagine that, right? The change in the frequency sort of stretches out the sine wave or compresses the sine wave. Change in the phase shifts the sine wave. And those two things correlate with one another, just like kind of the lifetime of the exponential would correlate with the normalization of the exponential. The phase and the frequency of the sine wave correlate with one another. And this is the correlation between the frequency and the phase in my fit, right? Is the best fit result for those two parameters. But again, you see these kind of oval shapes. Here you see the high walls of the high square landscape, and it reflects that. You see these correlations. Then you would see it in the covariance matrix too.